Hi there, I'm Terry. Welcome to a much longer than 5-minute velo. In my last video I talked about seat pin failures, and there's a link to that video in the top right hand corner. Perhaps in that video I should have stressed, excuse the pun, that failure is not common. Although I have had 3 seat pins fail under me, that has been over 40 years and over 500,000 kilometers of cycling. In all 3 failures I didn't fall off. Although it doesn't happen very often, I'd still prefer that it didn't. It's not a very pleasant experience. Although I'm talking about seat pins, it's also an example of how modern engineering techniques can be used to structurally design components. My apologies to any engineers that may find this oversimplified. My new gravel bike frame set came with a seat pin. As it's a budget frame set, the seat pin is probably not of the highest quality. While building the bike, I might as well try and take steps to reduce the likelihood of failure. My seat pin is round and 27.2 millimeters in diameter. Other shaped seat pins, like this one on my Giant Defy, or larger diameter seat pins, are much less likely to fail. My 100 kilos of mass is probably also not helping. In this video, I'll show some engineering analysis to try to quantify the benefit of a double seat clamp like this one. I'll be comparing it to this single original clamp that came supplied with the frame set. This won't be a comprehensive analysis, it'll be a comparison of the 2 types of seat pin clamps, and the results will be more indicative rather than predictive. In my last video, I showed some hand calculations based on beam bending theory. The beam bending theory doesn't take into account some of the more complicated aspects like contact, stress concentrations, etc. In this video, I'll show you some finite element analysis that can consider more of the detail. However, I should stress it's not perfect. There are still simplifications. I started off by building some CAD models of both clamp types. The original clamp that you can see here, and the double clamp here. Once these were produced, I could send them over to the finite element model simulation program. Here I took advantage of symmetry and cut both models down the center. I put the appropriate boundary conditions on that cut center line and in a couple of other places. These blue arrows represent the forces created by the seat clamp collar bolts, and these arrows on top of the seat pin represent my weight. I've invoked St. Venant's principle and simplified the geometry at the top of the seat pin. There are contacts between the seat pin and the seat clamp, so those regions have the capacity to separate and slide as needed. I'll carry out the analysis in 2 distinct steps. The first step will have the seat clamp bolting loads only, and the second step the bolting loads plus the rider weight. I'm going to start by looking at how the models will predict how the seat pin and seat pin clamps deform. This will tell me whether I've made any major mistakes in the modelling. We'll start with step 1, that is bolting loads only. Here we're looking at coloured contours that indicate how much the model is deformed. As there's no rider load on here, we wouldn't expect the seat pin to deform very much. And indeed, this green colour relates to less than 0.4 of a millimetre. In addition, we can visualise that deformation by putting a deform plot on. This is obviously magnified many times. If we look front on, we can see the lines of symmetry down the centre of the seat post remain flat. Whereas you can see the clamps, where they've been pinched up, have deformed. Remember, the deformed shape is shown magnified. If I switch the magnification deformation back to full size, you can hardly see any deformation. Let's look at the deformed shape plot for step 2, with both the clamping loads and the rider loads. The contours have been redrawn, and you can see the maximum deformation takes place at the top of the seat pin, and it is just about 3 millimeters. This is in the ballpark of what I might expect. The centerline boundary conditions on this step were good too. I can further illustrate how the models will deform by animating them. If you look in here in a bit more detail, you can see the mesh that I've used. For clarity, I'll turn that off now. Let's have a look at the deformation of the seat pin where the seat clamp is. In both cases, you can see where the seat pin is being constricted by the seat clamps. So the clamps are doing their job. They're squeezing down onto the seat pin. And these give rise to frictional forces, which prevent the seat pin sliding into the frame. Overall, the deformations look realistic, which gives confidence that the models are behaving as we would expect. Now, let's take a look at the stresses in the two seat pins. I've assumed the minimum material strength is around 500 newtons per millimeter squared. In reality, this is probably a bit low, but it's a useful value to start the analysis. I'm still showing contour plots, but now of the first principal stress. I've scaled the contours so that anything in red is above 500 newtons per millimeter squared, and anything in dark blue is lower than minus 500 newtons per millimeter squared. So any regions of the model that are either in red or dark blue have the potential for material degradation or even failure. Let's start off by looking at step 1, that is the collar clamping loads only. So there's no rider weight on the seat pin yet. Externally, as you can see, there don't appear to be any red or blue regions. However, if we turn the model around so we can look on the inside of the seat pin, as you can see here with the original seat pin collar or clamp, there's a region of red inside the seat pin. Inside the seat pin on the double clamp model there's also this tiny region of red. However, the red region on the original clamp is much larger, suggesting that local stress is somewhat higher. So why are there regions of high tensile stress on the inside of the seat pin? For clarity, I'll hide the clamps. Now if I rotate this round, we can look at the outside of the seat pins, and as you can see, there are regions of compressive stress. This is not really surprising, as that's where the clamps bear down on the outside of the seat pins. To help explain, I'll turn on the deform shape plots. The deformations here, obviously, are highly magnified. Now you can clearly see that the seat pin clamps are constricting the seat pins. Those constrictions give rise to localized bending stresses. On both models, this is clearly exacerbated by the slot in the seat clamp. The corners dig into the seat pin. However, on the original single seat clamp, the forces are obviously more concentrated. They're less spread out. Whereas the double seat clamp, those forces are spread over a larger area. And as you can see, the constricting deformations are lower, giving lower parasitic bending stresses on the inner surface. I'll turn off the deform shape plot. Similarly, on the front of the seat pins, on the outer surface, that clamping force is inducing a slight compressive stress. Just as a reminder, there's no rider load on this. This is also true on the double seat clamp. You can see areas of compressive stress. These are a bit lower than on the single seat clamp, but that's to be expected as the loads are spread over a much larger area. Let's look at the front of the seat pin on the inside surface. So as not to violate local equilibrium, if there are compressive stresses on the external surface, there must be tensile stresses elsewhere. And indeed, looking on the inside, there are regions of tensile stress, as indicated by these yellow colors. I'll just turn the clamps back on so you can see where the seat pins are in relation to those clamps, and which clamp is which. I can use a probing tool to inspect the actual values. For the original single clamp, the maximum stress on the inside surface is 314 newtons per millimeter squared, so well below the failure strength of the material. If I look at a similar position at the top of the double clamp, I'm getting a value of around about 130 newtons per millimeter squared, so quite a lot less than in the single clamp. However, that's not the highest stress region according to these color bands, so let's look lower down. So the maximum tensile stress on the inner surface of the double seat clamp is around about 300 newtons per millimeter squared. A little bit lower than the single clamp, but not substantially. So under the seat pin clamping load only, the most significant regions seem to be on the inside surface at the back of the seat pin, where a slot in the seat collar causes a stress concentration. I'll probe the actual values to compare the two different seat clamps. For the original single seat clamp, I'm getting a value of about 750 newtons per millimeter squared. Whereas on the double seat clamp, the maximum is about 525 newtons per millimeter squared. Some models are predicting that damage could start to occur on the inside surface at the back of the seat pin, caused by the clamping load only. As expected, because the clamping forces are distributed over a wider area, the double seat clamp induces lower stresses into the seat pin, and therefore the seat pin should be more reliable. Let's move on and look at the seat clamp loading plus the rider weight. To illustrate both loads, I've turned on the deformed shape plot again, obviously exaggerated. I've kept the scaling on the coloured contours the same, so anything in red or dark blue is a potential area where degradation or failure could occur. Again, looking around the outside of this, I can't see any red or dark blue. However, let's look on the inside again. I'll just turn the deformations off to make things clearer. We can still see that there's a red region inside the seat pin that uses the original single clamp. That small red region on the inside of the seat pin with the double clamp seems to have disappeared. I'll hide the clamps and put the deformations back on. The deformations around the clamps are pretty much the same as the deformations in the previous example with the clamp load only. The only difference here now is the seat pin is bending. I'll turn the deformations off again. Looking at that red region, there doesn't seem to be a lot of difference. However, if I put the probe on there, it's now about 660 newtons per millimeter squared, whereas previously, with the clamp load only, it was about 750. That's because the rider weight is bending the seat pin, and therefore putting the back of the seat pin in compression and the front in tension. So at the back, we're adding a compressive stress to the existing tensile stress in that region, which reduces the tensile component. However, the damage may have been caused by that clamping load, and putting the rider weight on there won't undo that damage. When I started this modelling work, one of my preconceptions was that the most critical area would be at the front of the seat pin, just above the top of the seat clamp. What I was expecting, because the rider weight causes a tension at the front, there's a geometric discontinuity here that will cause a stress concentration, and therefore there would be a high stress in that region. As you can see, there's no red or dark blue in that area. What we saw with the clamping load only is the clamp constricts the seat pin, causing bending stresses, and therefore puts a compressive stress on the outer surface just above the clamp. In reality, all that's happened is the rider weight has reduced the compressive stress in that region. If I hide the clamp, you can see there's a light green shade around there, which is actually a very low stress, less than 71 newtons per millimeter squared. So that was a surprise to me. If I go to the double seat clamp model and hide the seat clamp, you can see it's pretty much the same on the outside of the seat pin. Very low stress, although there is a region of slightly higher tensile stress down here. So the same is true on the single seat clamp model. So I can probe the values there, and we find that they're around about 260 newtons per millimeter squared. Higher, but still not really high enough to do any damage. On the double clamp model, the maximum's about 235 newtons per millimeter squared. Because I said the clamping forces caused a constriction of the seat pin and induced localized bending, then if there are compressive stresses on the outer surface, there must be tensile stresses somewhere else in order to maintain equilibrium. Indeed, if we look at the front of the seat pin on the inside surface, we can see some tensile stresses. I'll just show the clamps in the models again so you can get an idea of where those regions are. So let's probe the values on the inside of the single clamp seat pin first. The maximum values are around about 385 newtons per millimeter squared. Let's look inside the seat pin with the double clamp. So we have a maximum value of around about 375 newtons per millimeter squared. Although the double clamp seems to have reduced the stress on the inside of the seat pin over that of the single clamp, the difference doesn't seem that great. The good news is that in both cases, those maximum stresses at the front of the seat pin are quite a lot lower than the strength of the material, and therefore are unlikely to cause damage. I found that the seat clamp bolting loads induce the highest stresses into the seat pin. These were particularly acute around the slot in the collar, and those clamping stresses will contribute most to any potential failure. For this reason, it's probably sensible to abide by any seat bolt torque settings, although maybe that's just common sense. I found the double collar spreads the bolting loads and hence reduces the stresses associated with the collar, which will reduce the likelihood of failure. Although rider weight does induce some stresses, they're relatively low compared to the seat bolt clamping stresses. I must admit, this is not what I was expecting. In this analysis, I've only considered static loading and linear material and geometry responses. However, fatigue could be an issue. That is, repeated loading that causes material degradation. So if you're one of those people that has to keep tightening and loosening the seat pin clamping bolt, say for instance to put it in a car, then you might want to pay particular attention to the clamping loads caused by tightening the clamp collar bolt. My advice would be not to put the seat clamp collar on backwards like this, as the region of high tensile stress associated with doing the clamp up will move from the rear of the seat pin to the front. The tensile stress associated with the rider load can then add to that peak stress, increasing the highest stress even more. To illustrate that, here I'm comparing two different models. On the left is a model with the seat clamp collar bolt to the rear of the seat pin, and to the right a model where the seat clamp collar has been reversed and the bolt is at the front of the seat pin. On the left, the maximum stress is 750 newtons per millimeter squared, whereas on the right, it's 840 newtons per millimeter squared. So putting the collar on in the reverse direction substantially increases that localized maximum stress. If you haven't done so already, please consider subscribing by clicking on the 5-minute Velo logo. If you think this video is not too long and you appreciate this sort of content, please give it a thumbs up. Obviously, if it's too long or the content's not to your liking, give it a thumbs down. If you'd like to leave a more nuanced answer, leave a comment. From me, for now, it's goodbye.